Okay, so let us begin today's session. Uh, I would ask you to just keep a pen and paper handy so that we can also do these derivations along. Um, okay, so for this session we'll be doing some problems on Kubo formula. So you already heard about Kubo formula. So let me just give you a very brief and very simple recap of what a linear response is. So for example, let's say I have some Hamiltonian. So this is a very small introduction of linear response. So let's say we have some Hamiltonian H, okay, and we want to study its various properties, right? So when we try to do that, what we normally do is we try to do different experiments. So that means we will apply some different, let's say, electric field or magnetic field or some external kind of perturbation that will change the Hamiltonian somewhat, and we will try to see that what is how does a observable change, and that will give us a lot of information about the system. Okay, so that by that I mean that I, on top of this H naught, I have additional some force which couples to some other operator which we call here as B. So this is my total Hamiltonian. So let me give it a suffix and write it as H suffix f of t. Okay, so now this is my total Hamiltonian. So now I am asking the question, how does the expectation value of this ft that changes. So basically I am asking what is the expectation value of a minus a of 0. So when there was no external potential or external disturbance. Okay, so this is, so the answer is given by linear response. So in linear response you then convert all of these things into interaction picture, and you try to do a perturbation with respect to this small external parameter. So let's say the f is very small compared to the characteristic energy scales of your system. So then we like to do some perturbation in this, and we would like to retain the linear term of that perturbation series. So in that sense it is just a linear response. Okay, so the expression of this is kind of simple. So this is given by some function chi a b function of t, and then there is this forcing term t minus tau and dt. Okay, and there is some integration 0 to infinity or some minus, or you can also keep it minus infinity to infinity as well. So this you see that so this is a linear in force, right? So linear in force. Okay, and there is a coefficient. Now this coefficient is really interesting because all of the information about the system is included in this thing. So depending on what is the observable A that we are choosing, and what is the operator B that the external field couples with, we can ask different question and can get a sensible kind of answer. Okay, so let me show you how does this calculation go, like how does the chi AB looks like. So generically a chi AB, so it is a function, it is a function of these two times. Okay, generically it is a function of 2t and t primes, and the expression is given by, I mean, after doing all of this perturbation theory and all, you will get the expression which is theta t minus t prime, and there is the expectation value of a commutator bracket between at and bt prime. Okay, so this is how the chi looks like. So this is also often called the susceptibility. Okay, chi is also called the susceptibility. So this is all that we need to calculate. Okay, so now, so let me first show you for a simple case how do we go about this calculation. Okay, so we will assume that our Hamiltonian can be written is a diagonal Hamiltonian. So I'll be doing everything in second quantization, and that makes all of this calculation very kind of simple, right? And So, and at any point if you have any questions, please feel free to ask. Okay, so I would like this session to be very much interactive, and you can ask any other questions as well. Okay, so let's assume that the Hamiltonian is a diagonal Hamiltonian. So by that we mean that we can write the Hamiltonian by something like this. So some C lambda dagger C lambda. So you will identify that this is a second quantized Hamiltonian and looks much like a kind of a harmonic oscillator, right? When you diagonalize the harmonic oscillator and you write it in terms of ladder operators like A dagger and A, then the Hamiltonian actually takes a diagonal form and it looks something like this, right? And the A and B, to simplify our lives a little bit, are also single particle operator, and you can write this operator in that eigenbasis of this of the diagonal Hamiltonian. Okay, so a generic form of this will be some matrix element A alpha beta, and then there is this creation and annihilation operator, so C alpha dagger and C beta. Similarly, we assume that B is also a single particle operator, which also has this kind of matrix element alpha beta, C alpha dagger, C beta, and summation over alpha and beta. Okay, so these are all of the things that we need to calculate this chi. Okay, now so let me show you how do we go about this calculation. So let's start calculating this. Let's call it equation 1, and we will do it here. So in the equation 1, so let's try to simplify things a little bit. So chi AB T and T prime. Okay, and so minus I by h bar. So for now let me say that h bar is equal to 1. So I am working in a dimension in a unit system where h bar is 1. So this is called a natural unit system. Okay, at least in condensed matter. So minus I, and then I have this Heaviside theta function t minus t prime, and then there is this expectation value. But as I have said that I will plug in this expression of A and B operator, right? So then I will have some summations, some dummy indices alpha beta, let's call them gamma and delta. Okay, because we love Greek variables so much. So now, so A alpha beta and B gamma delta, and the rest of the things you plug in. So these are C alpha dagger T, C beta T, comma C gamma T dagger C delta T. Okay, so now a commutator bracket of that, and then we will take an expectation value on the ground state. Okay, on the many body ground state or something like that. So okay, so the second C's are actually with a T prime index, because the definition was something like this. So B has a T prime argument. Okay, so now the task is to simplify the commutator bracket. Okay, but before, so you notice something interesting, that so these C's are actually the eigenbasis of the Hamiltonian. Okay, so in that case the time dependence of those C's are actually well known. So so if you remember, the time dependence are actually given by something like this: minus I epsilon alpha t for the alpha-th quantum number or alpha-th state with C alpha, and similarly the C alpha dagger t, so the Hermitian conjugate is given in terms of I epsilon alpha t and C alpha. Okay, so so now we can extract out the time dependence and simplify things a little bit. So let me just box it. So now this susceptibility, it looks something like this. So chi AB T and T prime minus is equal to minus I Heaviside theta T minus T prime, and then there is all of this summation over Greek variables A alpha beta and B gamma delta. And so the time dependence looks something like this. So let me write in a single step. You can verify this easily. So epsilon alpha or epsilon alpha minus epsilon beta t times e to the power I epsilon gamma minus epsilon delta and t prime. Okay, and then so you can verify the time dependence. It is easy to check, and then we are left with only the equal time commutator bracket and the expectation of that particular operator. Okay, so now so what we will do is we will use a very useful identity of this commutator brackets. So let me first write it down. So if we have a four operator commutator, something like this, then you can actually write it in terms of anti-commutators in this way. Okay, so this is a very useful identity. Just keep, this makes many calculations very simple. So we'll use this identity on this commutator bracket. So the commutator bracket reads C alpha dagger, C beta, and C gamma dagger, and C delta. Okay, so now let me just denote this by ABCD so that it is easier for you to calculate this. Okay, so now we see that, so the first term is A, anti-commutator of B and C. So that means anti-commutator of these two objects. Okay, and we know that when you have a creation operator and its dagger and you take a commutation, then that is actually a delta, Kronecker delta, right? But on the other hand, if you have anti-commutations of only creation and creation operator and only annihilation and annihilation operator, then that results in 0. Okay, so being that said, so let me write this and it will be clear eventually. So the first term is C alpha dagger, and then B and C is denoted by CB and C gamma dagger, and then there is this only C delta. Okay, so the next term is A comma C, so that is C alpha dagger and C gamma dagger times BD, C beta, and C delta. Okay, so let's write all of the terms first, and then we will see which things stay and which things just vanish. So then we have C gamma dagger and C alpha dagger, and then C beta and C delta, and the last term is given by C gamma dagger, anti-commutator of C alpha dagger and C delta times C beta, right? So now if you know this fermion anti-commutation rules, it will be very clear to you that whenever you have anti-commutation of creation or annihilation, that is essentially 0. So that goes to 0. So the second term and the third term, that is essentially 0. So that is essentially essentially 0. Okay, so for the other two anti-commutators, we can actually replace this with a Kronecker delta, right? So the result would look something like this. So delta beta gamma C alpha dagger C delta, and so the second term and third term is 0. So I will directly go and write the last term, which is delta alpha beta C gamma dagger and C beta. Okay, So the commutator actually at the end of the day looks kind of simple. It is not that much horrifying as it was looking just a bit ago. So, and if we take the expectation of this whole thing, because you see that you have to take the expectation at the end of the day of this commutator bracket. So let me just quickly write these things. Okay, so the expectation would be something like this. So delta, beta, gamma, and C alpha dagger, C delta, minus delta alpha beta, C gamma dagger, C beta. Okay, so the commutator, so the expectation is like a linear operation, and it actually acts on each of these things, okay, term by term. So the this expectation values, because these C's are already in the eigenstate, so this expectation value will be only non-zero if the alpha and delta are same. Okay, and if the alpha and delta are same, then that is just an the expectation value just gives you the number operator of or the occupation of that particular state. Okay, so that means this thing will be simplified to delta alpha delta and the occupation of, let's say, level alpha. Okay, so n alpha here is just this quantity, C alpha dagger, C alpha. So that means that is the number operator corresponding to the quantum number alpha. Okay, or for fermionic system, what is the number of fermions in that particular alpha? Okay, so that kind of expectation value. And for fermion, you know that this can take either 0 or 1. Okay, and for finite temperature, it actually goes smoothly. Okay, it changes smoothly. It can take also in between. It can take half, some 0.75, and also some any floating point numbers. Okay, and the second term will be delta alpha beta and delta gamma. So okay, it is actually a gamma and delta. So that was a typo. So delta gamma delta, and then let's say n of let's say gamma. Okay, so now this is the, I mean, so okay, so we got something. So now we'll try to put this back in this expression. Okay, and we will do even more simplification. Okay, so let's call this equation 2, and we will just plug that whole thing in. So equation 2 follows. So chi AB function of t comma t prime is given by minus I heaviside theta t minus t prime. Okay, and then there was this summation over all of these Greek symbols, alpha, beta, gamma, and delta, and matrix element of all of these single particle operators. So there are some exponentials. Okay, so some exponentials. So let me just copy this part. And times this quantity. Okay, so this is now the whole thing. So let's do this summations term by term. So the first summation, so this first summation, so that actually gives me that sets some constant. So that says that my gamma would have to be beta. So because of the Kronecker deltas, so my gamma has to be beta, and this delta has to be alpha. So we'll use that to do the summation for the first term, and the second summation tells me that alpha has to be beta and gamma has to be delta. Okay, something like that. Okay, so yeah, seems okay. Yeah. So now if you just do this summations, you will see that you will get this and let's say uh, I'll do summations of over two variables, and I'll just keep two variables. So that means, so let's say for the first term we just keep alpha and beta. Okay, so if we just keep alpha and beta, so the first term actually simplifies to be a alpha beta b, then so gamma is replaced by beta and delta is replaced by alpha. Okay, and for the time dependent terms, so it is just e to the power I epsilon alpha minus epsilon beta times t, and times e to the power I epsilon beta minus epsilon alpha t prime. Okay, so you can combine both of these exponents, and you will see that you get a t minus t prime, okay, for the first term, and then the rest of the term is n alpha. Okay, so that is the first term, just the first term. So now we are left with the second term. Okay, so the second term will be given by, so a, so I think I have done some mistake in this second term, so let me just quickly go back and see. Oh yeah, yeah, so second term, yeah, I have just actually messed up the commutator, this anti-commutator. So the anti-commutator has this Kronecker delta, which is alpha and delta in the Kronecker delta, and then there is C gamma dagger and C beta, yeah. So let me fix this quickly. Alpha delta, and then it becomes gamma beta, and let's call this n beta. Delta gamma beta n beta. Okay, so yeah, now it will work out. So the second term tells me that I have to replace delta by alpha and gamma by beta. Okay, so I'll do that. So I will have alpha beta and b, so gamma will be replaced by beta, and delta will be replaced by alpha and alpha. Okay, so you see that this actually comes in a kind of matrix product form. Okay, so when we have two matrix multiplication, let's say if we have matrix multiplication m times n, which is, let's say, which is some matrix P. Okay, so if I ask what is the ijth element, so then you will give me the answer that it is some I times k and n times k times j when I have a summation over k. Okay, and so you see that this actually turns out to be something like that, something like a matrix product. Okay, I mean, which is a nice thing. So the next term has a overall minus, and similarly it will have e to the power I epsilon alpha minus epsilon beta t minus t prime. Okay, and then you will have n beta. Okay, so these are the two terms that you will have. So we have simplified a lot. So let me write keeping this all together in a simplified manner. So summation over only alpha beta. So there was initially summations over 4 variables, alpha beta gamma delta. So but we have reduced it into alpha and beta using some properties of these operators. So coefficient a alpha beta and b beta alpha, and n alpha minus n beta, and you have e to the power I epsilon alpha minus epsilon beta times t minus t prime. Okay, so now you see, I mean, there is an interesting thing that you can observe here, that this actually is a function. So chi, so which I wrote as a function of t and t prime separately, is now seems like it is a function of t comma t minus t prime. Okay, so t minus t prime appears only here. Okay, and you will see that this will be always the case whenever you have a system which doesn't have some explicit time dependence. Okay, so always true for time independent system. Okay, so now this is, I mean, this is the full information of how the chi looks like in terms of these times. So let me write as t minus t prime. Okay, but it is sometimes it is very useful to go into the frequency space by performing a Fourier transformations. Okay, so the Fourier variable of t is actually omega. Okay, and we'll see that in the omega space or in the frequency space, this chi AB has all of this information that you can extract from this Hamiltonian, from this kind of I mean experiments. Okay, so to do the Fourier transformation, what we will do is, so let me just write the formula of Fourier transformations. So chi AB, a function of omega, is a Fourier transformation. So Fourier transformation is given by I omega t and chi AB function of t and dt, and the integration goes from minus infinity to infinity. Okay, so this is the standard Fourier transformations. So I have actually missed this 1 by 2 pi, but that 2 pi I will absorb in the reverse Fourier transformation, so that this total thing is 1 by 2 pi is conserved. Okay, so in the condensed matter, this is always we do. So to calculate omega, we will not add any kind of 1 by 2 pi. Okay, 1 by square root 2 pi. So let's do this calculation. So let's first just look at the time dependent part, right? Because all of the other things, the summations over alpha beta, those are time independent, and we will at the end we will just put everything together. So time dependent part is just theta t minus t prime. So I will also keep the minus I, and e to the power I omega plus epsilon alpha minus epsilon beta. Okay, so I'll keep another convergence. So this is called a convergence factor. And so delta is actually a 0, very plus, I mean very small positive number. Okay, so that actually gives some nice I mean nice way to calculating this, so that you don't have to worry how does this go as we go to as the t goes to infinity, right? So because you see that this is an oscillatory function, and to get some kind of solution, we need to truncate that oscillation. Okay, and what this I delta at the exponent does is, when t is very infinity, okay, then you see that this is just I mean this exponent is just become minus delta t. Okay, so whenever t is infinity, so delta is actually very small. Okay, very small. Okay, so that it makes it a e to the power minus actually so very small number. Okay, so minus some, let's say some constant. Okay, and you see that actually goes to 0 very fast. Okay, so that is what the convergence factor does, and that is the trick that we always use in many body physics or in quantum field theory calculations. So now we can do this integration. So the integration is just a simple integration of exponential, and you all know that this is given by so denominator gets the phase factor of exponential, and on the numerator we have e to the power I omega plus epsilon alpha minus epsilon beta plus I delta. Okay, and limit goes from 0 to infinity. So here also note a thing, that because of the presence of this Heaviside theta function, so you can actually write this integral as a 0 to infinity. Okay, and you can remove this Heaviside theta function, right? Because the Heaviside theta function is just it becomes 1 when the argument is positive. So that is one simplification. Okay, so now let's put together all of the limits. Okay, so now you see that whenever t is infinity, so as I put the convergence factor by hand, so then at infinity it just becomes 0. Okay, so it is not oscillatory at t infinity. Okay, and then we have minus 1 by I omega plus epsilon alpha minus epsilon beta plus I delta. Okay, and so remember that there are also other stuffs, right? So other stuff in this integration, but we are not thinking about that for now, but we will just put them together at the end. So some numbers. So the result is 1 by omega plus epsilon alpha minus epsilon beta plus I delta. So let's put everything together to write the chi AB as a function of omega. So now this is just simply a summation over alpha beta, and there are these matrix elements of this A and B operators, A alpha beta, B beta alpha. Then on the numerator you have n alpha minus n beta, okay, and then in the denominator we have omega plus epsilon alpha minus epsilon beta plus I delta. Okay, so this is a full result. Okay, so this gives us a full response for non-interacting system. Okay, so now this is what we are interested for now, at least. So now it has interesting properties. If you look at minus of imaginary part of chi AB, so that actually looks kind of interesting. So to calculate this, I'll be using something some formula, so which is given by omega 1 by omega plus I delta, and you can write that as a principal part of 1 over omega sum minus I pi delta of the full numerator without the this small I delta. Okay, so this is true in the limit when delta is 0 plus. Okay, so yeah, so I'll be using that. So let me just box it. So this is given by alpha beta, A alpha beta, B beta alpha, and then there is n alpha minus n beta of the numerator, which stays as it is, and the delta of omega plus epsilon alpha minus epsilon beta. Okay, so I've just followed the formula, and there is a pi multiplication. So this is the imaginary part of a correlation function between two operators A and B, and you will see that this has a lot of information. Okay, so first of all, so this part, okay, so this is actually occupation of occupation difference between two levels, alpha and beta. Okay, so for example, so let's say you have this alpha and beta, I mean in two levels alpha, let's call them alpha and beta. Okay, and let's say so there can be many scenarios. For example, so let's say this is your Fermi energy, because we are talking about fermions. So this is your Fermi energy. So Fermi energy is what? So Fermi energy is the energy level below which all of the levels are filled. Okay, so or you can say that Fermi level is the level up to which the Fermi C is there. Okay, so below this thing, so there is electron in this state and electron in this state. Okay, this is fully filled. So then if for such a scenario we calculate this n alpha minus n beta. So for both of these cases, this is 1 minus 1. Okay, so this becomes 0. Okay, so it tells you, I mean, it actually effectively gives you the Pauli's principle back. Okay, so it tells you that you cannot actually do transitions from a state alpha to beta if both states are filled. Okay, so this is one scenario. So the other scenario that one can possibly have is the following. So let's say so these are my two states, alpha and beta, and then this is my Fermi energy. So if my states are above Fermi energy, that means there are no electrons in that state. Okay, so I'll directly write it as, so n alpha minus n beta is just 0 minus 0, which is also 0. Okay, so that also means that, okay, if you have some free states or states which there is no particle in that particular states, so you cannot do transitions, right? Because you cannot take some thing which is not there and put it on some other level. Okay, it is not just there. And the other interesting thing, so let's say you have some alpha and you have some beta. Okay, and then the Fermi energy is such that it lies in between those two states. Okay, so in that case what will happen is, So the lower state has a particle, but the upper state, it doesn't have any particle, right? Because it is above the Fermi energy. So in that case, you will see that, so the n alpha minus n beta is just 1 minus 0. So then that becomes 1. Okay. So you see that, so this actually somehow tells you that where the Fermi energy is. Okay. So it will be non-zero until you reach it will be 0 until you reach the Fermi level, and it will start becoming 0 if you just have transitions between the alpha and beta. Okay. So Sanjeev, I am just muting you. I think some background noise is coming from your side. So if you have any question, just unmute yourself. Okay. Okay. So the first term effectively tells, it can help you to detect the Fermi energy, right? So it will tell you when you can have some kind of this kind of transitions between alpha and beta. Okay. So this is the first information that you see from this very simple non-interacting picture. And the second is, so this delta omega plus epsilon alpha minus epsilon beta. Okay. So now what it tells you that, what this tells you that omega has to be same as epsilon beta minus epsilon alpha. Then only this correlation becomes non-zero. Okay. So how do we physically visualize this? So let's say I can try to draw states. So let's say I have some states alpha and beta. Okay. And so the constant that we have to have is that those states are on two different sides of the Fermi energy. Okay. And if I have some particle sitting here, okay, and then by some external perturbations, I am providing it some energy omega. Okay. So I am, let's say I am giving it some omega, which is like let's say my omega is this amount. Okay. So I am just providing it positive some omega. Okay. But you can see that this omega here right now is much smaller than the difference of this EB minus EA. Okay. So that means the transition will not take place. Okay. So to have the transitions between these discrete levels, you have to at least provide this amount of energy. Okay. So if you will be able to provide that amount of energy, which is same as EB minus E alpha, then only you can cause a transition and that particle will go here on the other level. Okay. So that is what the delta function tells me. Okay. So just to recap, so the two factors which this has so the first term is the difference of occupation, which tells me that the two states that I am thinking alpha beta has to be on different sides of the Fermi energy. Okay. And the delta function tells me that I'll have to at least provide it with this amount of energy to cause transitions. Okay. So in that sense, from this, these are really important information, and from this you can actually get some idea about its band structures and some particle hole excitations and a lot more. Okay. So with this very simple kind of correlation function or this linear response function, we can see that we can get some rich information about the system. Okay. So any question up until now? So if you get lost at any point, please stop me. Okay. So any questions, and please feel free to ask. Okay. Okay. So if you don't have any questions now, so for now what we have done is we have just started from some kind of a operators, right? So now let's calculate this for a many particle or many body system. Okay. So that we have some real space coordinates. Okay. So the system is kind of, it has some geometry and all. You can go to momentum space also. So here this is kind of a toy model just to show you some basic properties of the susceptibility of this linear response function. But so realistic systems has some also R dependencies. So you have to also think about the momentums also, right? So instead of this lambdas, these Greek variables, you will put the block momentum, because block momentum is a good quantum number when you have this crystal, right, crystal like systems. So okay, so let's try to calculate that. All right, okay. So there are many, I mean a whole lot of linear response functions. So one important linear response function is which is called a charge susceptibility. Okay, so which is given by something like this. So pi function of r and t is a commutator bracket of I theta t minus t prime divided by h bar, an expectation value, and commutator bracket of n. So n is a density operator, so I'll show you what that is. R t comma n r prime t prime. Okay, so these are actually so n's are density operators. Or to be precise, these are called charge density operators. Okay, so for charge you have to also multiply minus e. Okay, but so these are constants, so you don't bother about those now. So where does this function appear? So assume that you have some kind of a system. Okay, and you apply some external electric field. Okay, so the electric field enters the system, it does something linearly, it couples to some observable, and it does something to the system. Now if you ask, okay, in presence of electric field, what is the change in the this expectation value of this density operator? So that means, so what is so n expectation in presence of electric field minus n without the electric field. So now if you ask this question, linear response has an answer for you. So it tells you that this will be given by this pi function of r. So this will also now depend on r, right? So function of r t r prime t prime, and then there is integration over, let's say, this potential, okay, which is because of the electric field. So v r prime, so let's say r okay, so let's say yeah, so let's say r minus r prime and t minus t prime. Okay, and there is integration over dr prime and dt prime. Okay, something like that. So the linear response is given by this pi. Okay, so what is the change in expectation value of the density operator because of this new introduction of electric field is given by this whole thing, and the coefficient is the pi. Okay, and you will see that this also gives, I mean, us many interesting informations. Okay, so these kind of correlation functions, whenever we have this theta and all, so these are called retarded correlation functions. And in literature you will see that this is sometimes it is called a Kubo formula. So from this I mean all of this discussion, so I am trying to make you more familiar with the Kubo formula, so that if you want to, let's say, calculate some kind of a response or some correlation, then it is very easy. Okay, so it will be very easy for you to calculate any kind of response function if you would like to. So it turns out that the calculations are actually much more simpler if you go to the imaginary time representation. Okay, so in the imaginary time representation you will see that it has a very rich kind of a machinery, and all of the calculations that I have showed you as of now, it becomes much simpler. Okay, so I'll give you an example of how that happens. So just let me just formally introduce that. So r tau and r tau prime. So when we calculate in imaginary time, we will not calculate a retarded correlation function, but instead we will calculate something called a causal correlation function. So here I will have some time ordering, imaginary time ordering, and then n function of r tau, okay, and n function of r prime tau prime, okay. So you see that here I do not have any commutators, okay. So I have just two operators and they are time ordered product, and at the end I will take the expectation value, okay. So this is actually much simpler than this already it seems like that, okay. So now you can go ahead and try to calculate these density operators. So the density operators expression is given by, so let's say in r at time 0 is given by some creation operator cr dagger and cr, or if you like you can just write it as a field operators. So field operator psi at dagger and field operator psi of r, okay. So this is just the density operator, okay. And so you can go to momentum space and all, you can just do all of this thing manually, okay. So for that you have to use that the Fourier transform of this field operators is given by 1 by v summation over or 1 by square root v summation over k e to the power I k r, okay, and psi of or ck, okay. So you use that, you will go to momentum space, and things will become much simpler and very fast. But so let us not do that. So that is a manual labor that we are not trying to do here now. So we'll be a little bit smart, and we will be using Feynman's rules, okay, Feynman diagrams to calculate this. So how do we write a diagram for this kind of an object, this kind of expectation value? So so the idea is, first of all, let's identify what are the basic building blocks for our Feynman diagram, okay. So for the Feynman diagram we need to have this Green's function, okay. So Green's functions will be some line with an arrow, okay, and we also need something more. So we need actually a vertex. So this is the representation of n. So this n has this two arms, one is incoming and one is outgoing, and then there is one dashed line, okay. So the dashed line represents coupling with the external field, okay. So the charge so this is actually called a charge vertex, okay. So the momentums actually go like k comma omega goes inside here. So momentum and energy goes from one of the arm, and from this dashed arm, so the external field actually gives some additional momentum and frequency, okay. Let's call it q and capital omega. And then we have to, because at each of the vertices we have to conserve momentum and energy, so it is clear that the other arm has to give out q plus k comma omega plus small omega, right. So this is how the charge vertex looks like, and we have two of those charge vertices, right. So let me quickly write. So we have actually two of those charge vertices. So one like this, and we have another one, right. So let's draw that like that. Let's draw it like this, okay. So the task is to combine these things and get a scalar, okay. So everything should be contracted, and we should be able to get some kind of a number, okay, because you see that what we are looking for is actually a number, because everything we have taken the expectation value of everything, okay. So now what we will do is, so in this diagrammatic way we will just try to contract these two vertices, okay. So what option we have is that, so we have option, so which will be something like this, okay. Let me just draw a continuous line. So you can join these two and you can join these two, okay. So now you see that if you do that, and if we just assign arrows for this Green's function, you will see that this is actually a good way of connecting things, okay. But there is another way of connecting, which is something like this. So which is, let's say I will have something like this and something like this. Okay, and I will assign the this momentum arrows, and I will assign like this one. Okay, so now for this case, so for this particular case, you will see that so the connections can take place only when the momentum, the q momentum, which is provided by the external field, is 0. Okay, but for this kind of calculation, we do not want a q is equal to 0. Okay, so I mean so we'll yeah, so for now we are assuming that q not is equal to 0. Okay, so there are reasons for doing that, but so I'll go into that. I mean we will just slowly learn why that is true. So this is actually not permitted. This is not permitted for finite q. So that means we have to just work with this single diagram. Okay, so which looks like two Green's functions going and coming back. Okay, so let's draw this in a better way. So let me do a large diagram. So and I'll now write all of this momentum and energy vertices. So q omega goes in. Okay, and because there is no dissipation at all, so q omega has to go out. Okay, energy, because energy and momentum are conserved. And on the lower line, let's call this to be a momentum and frequency k omega, and on the upper line, let's call it k plus q and omega plus capital omega. Okay, so I mean this is how the momentums are distributed. Okay, so now what we will do is we'll just write the expression for this whole thing using the Feynman's rules. Okay, and I mean that's it. So we'll get the expression for that correlation. So this is how, I mean this is how things look like if you are working in a real time or real frequency domain. But again, so let me actually do this calculation in a imaginary frequency, or also called a Matsuura frequency, and that has its advantages, right? So I'll show you, I mean how do we do that. So for that, so you see that from starting from here, I have not done any simplifications of this, right? Simplification of this. So what I have done is I've just identified the basic building blocks of a Feynman diagram for this case, and I have just tried to connect all of the these legs. Okay, so I mean that is you do, I mean for calculating this response function. Okay, that is what you do. Okay, then so there is nothing more. So okay, so I was telling you that, so let's I was telling that instead of writing it in real frequency, let's write it in some imaginary frequency, also called a Matsuura frequency. So I omega n plus I omega n, and the lower line has only I omega n, and then I capital omega n goes out. Okay, so this I omega n, this is a fermionic Matsuura frequency. Okay, so why I omega n is fermionic? So because this is a frequency of a Green's function. Okay, so the Green's function is for fermions. So this momentum and this frequency are for fermions. Okay, so that means that I omega n will take values of 2n plus 1 pi I think kBt. Okay, and yeah, and so I omega n, so that is the frequency of the external field, and you can like in some way you can assume that this, because these are external frequency, are coming from some kind of photonic fields, right? So because electric field is just some photons, if you quantize that, it is just photons. Okay, So in that some pedagogical argument or some heuristic argument. So these are just some bosonic frequencies. So although that is, I mean, this argument is not true 100%. So but you can actually calculate and you can show that this the frequency that can come from here has to be a bosonic frequency. You can calculate that. Okay. For now, just believe me that these are bosonic frequencies. Okay. So this is a bosonic Matsuburger frequency. So then that means that it has to be 2n pi kBt. Okay. So yeah, something like that. Okay. So now we are at a position to draw this, I mean to calculate the this operator, I mean this Feynman diagram. So let us do that one by one. Okay. So so let me actually annotate different parts of this graph. Okay. So let's call this line as 1 and let's call this line as 2. Okay. And yeah, so that will be all. So now what we will do is, so we'll just obey Feynman's rules and we will just follow these lines, right? We'll follow this line and multiply in that order, I mean in which the arrow moves. Okay. So for the first line, I'll write a Green's function, which is a function of k, comma I omega n. Okay. So this is what I'm writing for just line 1. Okay. And then so I follow this line 1. I come here, I collide at this point. Okay. And then I have to move on to the next line. Okay. So for that line, I'll write as so this is for the other line. So I'll write Green's function, now which is a function of k plus q and I omega n plus I omega n. So I am just following this this momentum and frequency, right? So as simple as that. So at the end, when you are done with all of these things and you see that it actually comes back to itself. Okay. So whenever a line goes and comes back to itself, then that is actually that is what the trace is. Okay. So that is a trace. So I will take a trace of this thing. Okay. And so you see that the undetermined frequency and momentum are this k and I omega n, right? So because that goes inside the loop and that can be anything. So what choice you take? You take all of this choice and sum over, right? So I'll write it as a so I can write it as a discrete summation. So let's say k and I omega n. Okay, and we have some normalization according to Feynman's rules for imaginary frequencies, which is given by beta times v. So v is the volume of that system. Okay, and you see that because this is a fermionic loop. Okay, so this is a fermionic loop, right? And whenever you have fermionic loop, you just keep a -1 to the power number of fermionic loops. Okay, so here we have just one fermionic loop, so number of fermionic loop is 1. So we have just this additional -1. Okay. So now this diagram, when you write it, this diagram is this. Okay. So but we remember from the definition of this susceptibility that this causal this is called the causal correlation in imaginary time. Okay. So the causal correlation looks like this. Okay, and it has a additional minus to begin with. So what will happen is that additional minus will cancel this minus. Okay, and we have our full expression for this chi. Or the pi. So pi as a function of q and I omega n is given by this expression. Okay, so this is the full result that you can have. Okay, so now again so we will try to write this Green's function in a simpler way, and we will try to evaluate this this whole expression. Okay, so let's try to simplify this a little bit. So the first thing that we like to do is we like to get rid of this I omega n summation. So if you have attended the previous sessions, you will know that this I omega n summations are actually easy to do. So these are called Matsubara summations, and Matsubara summations are very easy way. So there is a nice analytical tool set that exists to do only this kind of summations. So we'll try to do that first. So before, the Green's function is actually, so let's first write it write everything properly. So let's say you have some block Hamiltonian and which satisfied this eigenvalue equation. So let's say u n k. So u n k are the block states, and these are your bands. So n is the band index, and E n is the value of that energy at that band, nth band, and momentum k, and then you end up with a nk. So this completes the eigenvalue equation for the Hamiltonian. Okay, so now if you know this so this is about the information about the spectrum, then you can write any operators in the basis of the spectrum, right? Because this U's actually they are a complete set of bases, they form a complete set of bases. So if you just take a outer product nk, okay, so only a summation over n, so that will be an identity. Okay, and let me write a k for suffix, so that will be identity for that particular k. Okay, so I mean, just to be a little bit concrete, so if you, so now the Green's function is also a matrix. So if Hamilton is a matrix, the Green's function is also a matrix. So the matrix is actually given by this simple expression. So for non-interacting Hamiltonian, it is just given by unk and unk, and then on the denominator you have I omega n minus energy of n and k. Okay, and you have a summation over all of the states. So this is the Green's function. Okay, so we'll use just this information and we will try to simplify this whole thing. Okay, so let's call this equation A, and this is equation B, and this is equation C, and let's say this is equation D. So now what we will do is substitute equation C in equation A. Okay, so task is simple, so let's try to do that. So now this is given by 1 by beta v, and then k I omega n, and inside the trace I will just put these expressions. So summation over n u n k and u n k outer product, and then you have I omega n minus epsilon n k. Okay, and on top of that you have another summation given by let's call that dummy index to be m. Okay, and so let's write that other Green's function. So u m k plus q, so the momentum argument becomes k plus q, u m k plus q, and in the denominator you will have I omega n plus I capital omega n minus epsilon m k plus q. Okay, so the trace of this whole thing actually. So trace of this whole thing. So I can so let's just bring the m here also in m, so that yeah, it becomes a little easier to write. So we see that there are these overlaps starts to appear, right? So let's then directly write this overlap properly. Okay, and so we will use the cyclicity property of trace, and I will send this this Kate matrix on the other side. Okay, so what will happen is so let me just make a copy of this. So I'll just use the cyclicity, and I'll take that to the other side. So I'll write UNK here. Okay, yeah. So now after doing this cyclicity, we see that all of these things are actually scalars, right? There is no matrix which is left here. So tracing of a scalar is just trace of some scalars. Let's say trace of 5 is just 5. So as simple as that. So we'll just remove this trace. So there is no trace anymore. Okay. So now things are a little bit simpler, and this kind of form actually we can do a Matsubara summation. We can do a Matsubara summation on this. Okay. But before, so let's organize this a little bit. So let's say, so let's call this as Fn m k comma q. So this is given by Unk um k plus q and mod square. Okay, so you see that this is just a mod square, right? So this is something, and the other thing is just the complex conjugate of that. So then that is just a simple mod square. So so let's rewrite this. So the denominator, so this upper part is just f in m k comma q. Okay, so the, I mean, you will find that this is sometime called as the form factor. So these are overlap of block states between different momentum points and between different states. Okay, so these are called form factors. And now let's focus on this Matsubara summation. So let's just write the Matsubara summation only, and then we will bring back together everything. So the Matsubara summation is just 1 by beta, and so there is I omega n summation and 1 by I omega n minus epsilon n k. So I omega n plus I n minus epsilon m k plus q. Okay, so now the first step is to write this. Okay, so to convert this whole thing into this integration. Okay, so for the simple integration, this is very easy to do. So there are no branch cuts, so there are only simple poles. So I'll just write all of this I omega n. I'll just replace I omega n by z. Okay, so this is what, I mean, for the simple case, this is what it boils down to. But if you have branch cuts, then you will have to be careful, and I mean there are some subtleties about that. So times the Fermi function. Okay, and so the rest of the term is the same as the previous line. So you just replace I omega n by z. So the first term becomes z minus epsilon n k. Okay, so the first term is just this one. Okay, so I have just replaced I omega n by z. Okay, and similarly the second term is 1 by z instead of I omega n plus I capital omega n minus epsilon m k plus q. Okay, so this is very simple, right? And so you immediately notice that, so there are two simple poles. So whenever z is equal to epsilon n function of k, so that is the pole, so which is coming from here. Okay, and the other pole is epsilon m k plus q minus I omega n. Okay, which is coming from this part. So these are the simple poles, right? And so now what we will do is, when we have identified the poles, we will use Cauchy's this contour theorem or the residue theorem, and we will do the integration. Okay, so what does that mean? So that means that, so this summation is just the summation over all of the residues. Okay, I mean, this integration is the summation over all of the residues. So, and for the simple poles, the residues are very simple. So summation over residues, and so let me write as f z, let's say z star. So z stars are the poles, so z star, and the residue of this rest of the part. So residue of this whole part. So okay, so let's try to write the what are the actually these residues. So then so what we have is f of so for the first residue, so then we will have this En of k. Okay, and then we will also have to multiply with z minus En of k. Okay, so that is what we do for a simple pole, and then we'll multiply this with 1 by this z minus En k. Okay, so let's first write it as this, so that each step is clear. So then on the this okay, so we have z plus I omega n minus epsilon m k plus q on the downstairs. Okay, so then after doing this, all of this multiplication, we will take the limit when z goes to epsilon n function of k. Okay, so first you see that this gets cancelled with this one. Okay, so then when you take the limit, then the limit just boils down to f of epsilon n k times 1 by epsilon n k plus I omega n minus epsilon m k plus q. Okay, so and so there is actually another residue also. So there is plus another residue. So let's do for that residue as well. So for that, so I'll directly try to write it. For that, so you have the inside the Fermi function, you will have epsilon m k plus q minus I omega n times 1 by epsilon m k plus q minus I omega n and minus e of n k. Okay, so when you take your time and calculate this, I mean, you will see that this is what you will get. So plus this another thing. So these are the two simple poles, so there is nothing left. Yeah. So there is a nice property of this Fermi functions. So if you have a Fermi function, some function of z, and if you shift this thing with some Matsubara frequency, you will see that because the Matsubara frequencies are even, so then that is actually periodic in the Fermi functions are periodic in this complex if you just shift it in Matsubara frequencies. Okay, so that we will use here and do some more simplifications. So then it becomes Fermi function of En k. Okay, so in the downstairs we have En k minus I omega n minus em k plus q. Okay, and we also have plus f em k plus q. So I am removing the I omega n because we know that is periodic. That is same as, I mean, up to any summation of I omega n. And on the downstairs we have em k plus q minus I omega n minus E n k. Okay, so this expression looks somewhat nice. So yeah, okay, so this is actually plus, yeah. So you see that both of these denominator actually look similar, but they are just different by a minus sign. Okay, so what I'll do is I'll just bring that minus sign here. Okay, and I'll write both of these denominator as the same. Okay, so you just combine this both of these things and you write it as f of E m k plus q. So forget about this, yeah. So now, so see what we have achieved now is, so we have started from so let me write this side by side so that you can appreciate it. So we started out with this Matsubara summations, okay, and from these Matsubara summations we could simplify things a lot, and after doing the summation, this is the simple expression that we have. So now let's pull everything together, okay, and so let me just copy this whole quantity. So now this was the whole pi q I omega n, right? And so I have done the Matsubara summation, so I will just remove this 1 by beta and I omega n. Okay, so all of these things will be gone. So and the things that will remain is just this quantity. Okay, so this is actually, I mean, this is actually the what you can do up, I mean, without knowing what the Hamiltonian is. So up until now, this is general and true for any non-interacting Hamiltonian. Okay, so any non-interacting Hamiltonian you can think about. So graphene or some 1D model, some Kita-F chain, some SSH model. I mean, this holds for everything up until now. So now if you want to do some more progress, you have to mention what are the wave functions, what are the energies, to do some more calculation. Okay, so we are not focusing on any specific kind of Hamiltonian. So let us try to see that without knowing any information about the Hamiltonian, what are the other things we can extract from this, what are the other things we can actually we can get to know about the system. So here I'll do one transformation. So I'll just change this I omega n to be some omega, or let's say some omega plus I times some infinitesimally small positive number. Okay, so this step is called analytical continuation. So analytical continuation in the sense that we have truly calculated a function for this imaginary variable I omega n. Now I am trying to convert that function into some real variable omega. Okay, so I analytically know a function for a particular domain, but I am trying to convert that for a different domain. So in that sense, it is called an analytical continuation. So that is a technical term. I mean, just in case if you just get across this technical term. So then if you do that, so then this q I omega n is written as pi q omega with a suffix r. Okay, so this means that this is actually retarded. So you remember that we started out with retarded functions. So retarded functions are what you have in real times. Okay, so retarded functions are when you have commutators and Heaviside theta functions, and those calculations are slightly complicated. But so this when you have these much lower frequencies, that makes your calculation slightly simpler. Okay, so at the end of the day, from this imaginary time representation, we can actually go we can actually go to this imaginary real time expression. Okay, so yeah, so that is something. So just 1 second. Okay, so yeah, so then let's convert it to a retarded function. So q omega, and then I have all of these things like 1 by v summation over k n and m states. So remember that we started out that we have a Hamilton which is a matrix, right? And so the summation goes over all of the states in m k q, and we have this f plus q. Yeah, so omega plus e n k minus e m k plus q plus some I delta. Okay, so this is how the retarded function looks like. Okay, yeah, so now we can look at the minus of imaginary part of this correlation function. So if you do that, so this looks something like this. So f n m, so f n m is real, right? So it is a mod square of some complex number, so it is real. So k comma q times f e n k to and e n k minus f e n k plus q, and times some delta function, Dirac delta function, omega plus e n of k minus e m of k plus q. Okay, and there is a pi multiplied. So you will see, see that in a like, so like I showed you for this single particle operator. So here also we see that this gives me a condition between so the transitions that the external perturbation induces has to happen between energy levels which are on two different sides of the Fermi energy. Then only this quantity becomes non-zero. So if like both of the bands are on the same side of so on below of the Fermi surface, then this and this are 1 and they cancel each other. If both of those are on the other side, then both of those are 0 and the whole result is 0, right? So then the n and m would have to be on different sides so that it can be either +1 or -1. And this delta gives me the condition that what is the amount of energy that I need to give from outside so that there is a transition, right? Because energy has to conserve, and this in quantum mechanics all of the states are discretized. So I will have to put only by that energy, right? So omega is that particular energy that that induces such transitions between two different levels. Okay, so yeah, so it turns out that there are some interesting things that happens for this charge correlations. So without going into much detail, so let me actually briefly tell you some story about what happens when you introduce interaction. So for now what we have been doing is everything is actually at the non-interacting level. So when you start putting in interactions, so then you have to do another perturbation theory in so perturbation theory in that interaction strength. Okay, so that actually is called a diagrammatic perturbation theory. Okay, So without going into detail, so let me actually quickly tell you. So we have seen that. So let's just draw diagrams, right? So in presence of interaction. Okay, so what happens that in presence of interaction, so I initially had only this this building blocks to build my correlation function, right? So one this, and the another was this one. Okay, but as soon as I introduce interaction, then there is one possibility of one new possibility of building block, which is the interaction line. So then, so this is one, and this is two, the second building block, and the third building block, which is not present for non-interacting Hamiltonians, so which is, let's say, the Coulomb interaction. So what is this Coulomb interaction? So that tells me that, so one electron is coming from here, and another electron is coming from this other arm. Okay, so they come together, so they they exchange momentum from this line, so some momentum will be exchanged. Okay, and after exchanging the momentum, the electrons go on their own. Okay, so this is what this vertex tells me. So now the task at hand is to make a permutation and combination of all of these vertices and come up with different combinations of diagrams that starts with this vertex and ends with this vertex, and in between you can put anything that you want. We have to obey like this. We can only put this kind of things. Okay, so 0th interaction order. We have no interaction, right? So which is a non-interacting limit. So we have only this, and we have only this, and we join this line. So we join, and this is called a bubble diagram, or a polarization bubble. Okay, so let me just write it properly. So this is called a polarization bubble. So this is what we have learned how to calculate. Okay, so this is the 0th order. So in the first order, what you can do? So in the first order, so we have this thing. So let me draw it, and then it will be easier. You see that, so what I have done here is, so with these vertices at the end, I have just introduced this interaction line, right? So this interaction line goes inside and gives me what will be the diagram in the first order in interaction. So you can do this game, over and over. So for example, in the second order, you will have this, then you draw another of this wiggly line, another of this circle, another of this circle, and then you end up with this external field lines. Okay, so here you see that I have inserted this is one of the vertex, one of the Coulomb vertex, and this is the other Coulomb vertex. So we have two of these Coulomb vertices, so that's why this is second order. Okay, so but this is not the only one diagram. You can have something like this. For example, something a little bit complicated, something as so one of this here. Okay, so this is a first order diagram. Okay, this is a first order. So I have inserted the Coulomb vertex here. Okay, so this kind of diagrams are these are somewhat complicated. So in the second order, you can have something like this. So let's say one of this here, and then one of this here, and then you end up with another bubble. Okay, so this is, you can have in second order. Okay, but these are really complicated diagrams and we do not want to go to these diagrams, so we'll only stick to this kind of diagrams. Okay, so diagrams which we can actually just combine together to get the higher order diagram. So you see that, so I have just made this twice, right? So this is like a GP series. So this so just putting this 3 times, so this is like a GP series, right? So it turns out that this also has a Dyson kind of equation. Okay, and so in this thing we'll just we'll just assume that these are not there. So we'll assume that these are we'll not take this into account. Okay, although those are there, so we'll not take this into account because we want to do some progress in calculation. So because the exact non-interacting interacting problem you cannot solve. Okay, so you have to do some approximation, and this is our approximation. Okay, so so what will happen is, so we will have a bubble, we have a polarization bubble. So now let me make it a dark bubble. Okay, so this is a field bubble. So this is interacting susceptibility. Okay, so this is, so so I am not drawing the external legs, but you can assume they are there, you can imagine that they are there. So this is given by this single bubble plus one bubble, Coulomb interaction, another bubble, one bubble, Coulomb interaction, another bubble, and it goes on, and this is an infinite GP series. Okay, so now we see that, I mean, if I just take this take this line and okay, so I mean, so let me write this first. So you'll see that I can basically write this thing like a recursive kind of a series. Okay, so if you just, so this means that, so if you put this back here, if you put this whole equation back here, okay, so then you will see that you will generate this full series. So the full series will be generated. Okay, so which you can try. So now so this is actually a Dyson series for these correlations. Okay, and it turns out that you can actually sum up this infinite series, because this is a GP series, right? So we know the formula for GP series, so you can sum up this whole series. So so let me write this left hand as W. Okay, so now these are function of Q and omega, and then I have pi, which is function of Q and omega, plus, so pi okay, so let me write it, okay, pi. So let me write this as pi naught. So pi naught means non-interacting polarization. So then I have pi naught non-interacting polarization Q omega. Okay, and then there is some V of Q. Okay, so V of Q is because of this line. Okay, and I would end up with pi of Q comma omega. Okay, so which is again the non-interacting the interacting susceptibility. Okay, so now let's try to solve and find this pi of Q and omega. Okay, so pi Q and omega, so let's try to bring this piece onto the left hand side. So then it becomes pi naught Q omega V of Q pi Q of omega is equal to pi naught Q and omega. So now you can see that I can actually take this pi common. Okay, so I have take this common Q omega, and now I can just invert this. I can bring this to here, right? So that will give me the solution. So pi Q and omega is given by so 1 minus pi naught Q omega V of Q inverse and pi naught q omega. Okay, so now this is the solution for a interacting susceptibility. Okay, so so this quantity is actually very interesting. So this quantity in the square brackets, so this is called the dielectric function. So this is called the dynamical dielectric function, so which is a function of q and omega. Okay, so this is so this is dielectric function inverse. Okay, so now if you plot this imaginary part of pi q omega with a minus sign. Okay, so you can plot this, right? So on one axis you have q, on one axis you have omega, and you do a density plot. Okay, so you do some kind of density plot, some contour plot or something. So that will immediately tell you that so there are whether there are some plasmonic modes or not. So plasmons are a collective phenomena. So when you have interaction, so then the interaction can give rise to collective phenomena, and plasmon is one of the collective phenomena. Okay, so plasmon are like some elementary electron hole excitations that you can think about. So you will get some somewhere you will get some peaks, okay, and somewhere you will get some zero values. Okay, and it turns out, so if you will get the zeros, if you will solve this, if you will find where this becomes 0, at which q and omega this becomes 0, you will see that will actually follow the maximas. Okay, so these are like single particle excitations in this thing. Okay, so this will give information about collective phenomena and also single particle excitations. So yeah, so this is really interesting and very handy to really look into some collective phenomena. Okay, so if you want to so this is some approximation we are doing, but this turns out to be quite robust. Okay, and experimentally what you get comes very similar to this kind of a approximation, this kind of a series. Okay, so this is a Dyson series kind of a thing. Okay, so in literature this is called a RPA, so random phase approximation. Okay, all right. Okay, so let's see what we can do next. Okay, so let me actually quickly tell you about conductivity. Okay, so you can get conductivity also from Kubo formula. Okay, so let's try to write here. So let's remember what is the Ohm's law. So Ohm's law is J, the current density. The current density is given by sigma times the electric field. Okay, so the sigma here is the conductivity. So what does that mean? So it looks like a linear response equation, right? So that means that if you apply some external electric field, okay, and if you measure the linear response, or if you measure the current, then the proportionality factor just gives you the conductivity. Okay, so so the conductivity can be written in terms of a correlation between current and current. So so because okay, so the electric field actually couples via so if you want to see the current response, the electric field couples via the vector potential. So in the Hamiltonian, the external perturbation looks something like J times A. Okay, so the external perturbation is that couples to the current. Okay, so naturally we're interested in a correlation function which looks something like this. So pi, so J, or let's say alpha beta function of r prime t prime. So this is a retarded function, so I'll write as minus I theta t minus t prime. Okay, so t minus t prime, and I'll write the expectation value of the commutator bracket. So j alpha r t comma j beta r prime t prime. Okay, so this is what the correlation is. So alpha and beta are direction x and y. Okay, if this is 3D, then also z. Okay, so this is what the correlation is. Okay, and this is related, I mean, this will give rise to the conductivity. So the conductivity, if you just you can show that conductivity as a function of just omega is given by some alpha beta, is given by uh, some I by omega times pi alpha beta omega q tending to 0. Okay, so this is what the conductivity is. Okay, so now so like last time, we can try to simplify this using this Wick's theorems. We can try to do these contractions manually, or we can try to do some kind of diagrammatics. Okay, so diagrammatics is always simpler to do because everything becomes visual. So it is, I mean, well, you're less likely to make some mistakes. So let's try to do this. Yeah. So you can show that the form of the current operator in momentum space. So form of current operator is given by k summation over states c k alpha dagger, and so block Hamiltonian's derivative, and the or let me write is a k m n k m, the mth element of this derivative times c k n. Okay, so this is how the okay, so this is actually k plus q n. Okay, so this is how the current actually looks like. So you see that, so this has this additional matrix element. So which was not present when we wrote the density operator in momentum space. Okay, so this is another degree of non-triviality added into this problem, right? So now, so to do the diagrammatics, so first of all we have to identify what are again our building blocks. So the building blocks here is a vertex of the current operator. So current operator, as any single particle operator, has two legs, one incoming, one outgoing, and there is another external legs that the external field couples with. Okay, so so these legs has k and omega. So external fields gives q comma capital omega, and then the third leg has q plus k comma omega plus capital omega. Okay, so this is how the current vertex looks like. Okay, so yeah, so now so for this, so this is actually, I mean, so for this vertex we'll write del h and del k. So this is the additional thing that you have to do when you are dealing with current operator. Okay, so let us quickly try to see the non-interacting correlation, current correlation. So for the non-interacting case, we only have two of these vertices, right? So this one and this one, and what we do is we just join this both of these lines. Okay, so this is called a current correlation. So let me draw a nicer diagram. So these black dots are current vertices. Okay, So now we can do the similar thing, but here we have to just mention that so these vertices are actually now matrices. Okay, so now that additional matrix will come into the this expression. Let me enlarge it a little bit. So how does the momentum and energy distribution look like? So it looks like something like k, some I, so let's say I omega n. So I'm already writing it in terms of Matsuura frequencies. So the external fields give some q comma I capital omega n, and then I have k plus q I omega n plus I omega n, and then q comma I omega n goes out. Okay, because energy has to be conserved, there is no dissipation. So now let's annotate this with different parts. 1. So now the vertex will have another contribution. This is 3 and this is 4. Okay, so so let's write as we did for the last time as well. So for the first line, I'll write k I omega n, and then I'll write the vertex. Okay, so the vertex is del h. So let's call this alpha and beta. So del h, so del h k del k alpha. Okay, so that is a matrix. So this is a matrix multiplication times just to be clear, so this is my 1, so this is my 2, and then I have this other Green's function, right? So the 3 Green's function 3, so which is g k plus q I omega n plus I omega n, okay, times del h, so del h k plus q del k beta. Okay, so now it comes back to itself, 3 4, so it comes back to itself. So as a result, we will take a trace. Okay, so we'll take a trace, and so we'll have to follow the other Feynman's rules as well. So there will be a summation over this momentums. Okay, so momentum k, and also summation over this internal frequency I omega n, right? So because the internal frequency and momentum has to be integrated over. So then there is 1 by beta v as a normalization, and you remember that because of a Fermionian loop we have a -1, but anyway the correlation function always had a -1, so that minus actually gets cancelled. Okay, so now this is your full correlation function, pi q I omega n, so alpha beta for these two Cartesian directions, x and y, or if you have 3D then 0 as well. So then you calculate this, okay, and then you divide with omega, that will give you the conductivity. Okay, so you can do the simplification, do all of the simplification, assuming that your Hamiltonian has some eigenvectors u and k. So the energies are E and k and u and k, right? And the Green's functions at k omega I omega n can be written as a spectral decomposition, sum over all of the states u n k, and then I omega n minus epsilon n k. So if you just take that and you do some simplifications, you'll be able to do the Matsubara summation. Okay, so then it depends on what specific system that you are looking at, then the calculation diverges from that point and it becomes precise for that particular system. Okay, so I hope you get some familiarity with how to deal with Kubo formula and how to deal with this kind of diagrams. okay, to calculate correlation functions, because the correlation functions are what we measure experimentally, okay. And I mean, it is important in condensed matter to learn how to calculate these correlation functions, okay. So I hope this lesson has been useful for you. So any question? So if you do not have any question, so then we'll end the session. So best of luck for your exams which are coming up, okay. So thank you for joining today, and I'll see you probably some other semester. So yeah, that will be all. Okay.